Now. There we are. Okay, good afternoon. Guys, got it? Okay. Can I start? Right. To start off, I'll just apologize for the level of the talk being more or less aimed at the third years that are not here today. So for those who know everything, excuse the basic introductions. What I'm talking about is the GAMKA array at iThemba Labs. This was established in a consortium between the universities of Western Cape, Zululand, Wits, Stellenbosch, and iThemba Labs. And the aim was to combine high resolution and high efficiency gamma detectors in a flexible configuration, increase the number of detectors that we had available. So the idea was to, and the detectors would include high purity germanium clover detectors with bismuth germanate suppression shields, lanthanum bromides, segmented germanium detectors, and then the whole system should also be able to accommodate ancillary detectors, like, for instance, silicon strip detectors inside the target chamber. So I'll start with an introduction on gamma spectroscopy and gamma arrays, then mention the possible frame designs, design parameters, show some giant simulations, and present the present status. At the bottom, you can see the principal investigators of the GAMKA proposal, led by Nico Orthe, who put in a huge amount of work on this project to get this funded. Yeah, this doesn't work, it seems. I'll just use the pointer. Right, detector properties. Your germanium detectors, at best, they give you a resolution of 2 keV at 1.3 MeV. The lanthanum bromides have a high efficiency, but the resolution is somewhat worse at 35 keV at the same energy. Then we have to take into account that in a nuclear reaction, you can have Doppler shifts and Doppler broadening. So is this working? Yeah, there's a pointer. So if the source is moving relative to the detector, you have a Doppler shift in the energy. But important for us here is that you also have Doppler broadening, because your detector will subtend a certain fixed angle, a certain angle that's subtended by the detector, and that will broaden your energy and add to the resolution. So this gets taken into account when you design the array. Efficiency is just the number of gamma rays detected versus divided by the number of gamma rays that your source emits. And that depends on detector material, energy, volume, distance from the source, and so forth. It's governed by the basic interactions of the gamma rays with matter, being the photoelectric effect that decreases rapidly with energy. That loses all the energy of the gamma ray in an interaction with a single photon. Compton scattering, the photon scatters off the electron, and some energy may escape out of your detector, adding to background. And then there's pair formation, where you produce an electron-positron pair. The combined effect of these processes give you an efficiency that is energy dependent. And for a large germanium detector, it will look something like that. For a smaller volume germanium, the energy dependence, the efficiency drops much more rapidly with energy. An important parameter also is the peak to total ratio, which is the ratio of the photo peak or the full energy peak over the total area in your spectrum, which includes this background section that comes from Compton scattering, where the scattered gamma ray escapes from the detector. Sometimes you also have the resolving power used as a parameter, which is really how good is the array at resolving weak cascades of a lot of gamma rays that have close energy separation. And this depends on the peak to total, the efficiency, and your energy resolution. So all of these things add into the resolving power. Where's this arrow? Right, just briefly on gamma spectroscopy. If you do a reaction, you can get a huge amount of gamma rays, and the aim is to try and construct a energy level scheme for a specific nucleus from the energies of these gamma rays. You have many gammas, and to do that, to construct this level scheme out of it, you need coincidences between gamma rays to select specific regions. So you can place a gate in it, then you will only see gamma rays that are in this section and not the ones that are in that part of the label scheme. So for an array of gamma rays, for a good gamma array, you need a large number of detectors, as many as possible, high efficiency, and you want to reduce the background, because as you can see, there's a large background under the spectrum there that come mainly from Compton scattering, and you need to try and reduce that as far as possible. So these are just nice pictures of some large arrays. Eurogam, Euroball in Europe doesn't exist anymore. It's been replaced. Gamasphere in the US is still active, has a large number of detectors. The most recent is Agatha in Europe, and similarly Greta in the US, that will contain a huge amount of detectors, segmented detectors with 6,000 plus segments in the whole array when it's completed. Smaller size in Canada, there's the Tigris array and the Griffin array, 16 clover detectors. The Aphrodite array at iThemba Labs had the same geometry configuration. The detectors were somewhat smaller, and until recently, we only had 9 detectors in that array. From there, we wanted to move to something better, improve on what we had before, and that was the aim of this GAMKA proposal. So the funding proposal involved getting 4 additional clovers, making 17 shielded clovers in total at iThemba Labs, 17 additional large volume lanthanum bromide detectors. In total, we would then have at iThemba Labs 23, and to build 2 frames to house these detectors in a suitable configuration. The aim was to have the frames as versatile as possible so that you could use it with a number of different combinations of detectors, shielded or unshielded clovers, plus large lanthanum bromides. We also have small lanthanum bromides that are good for time resolution, segmented planar germanium detectors. And in designing the frame, the important things is to optimize the clover efficiency of combinations of detectors, and also important is the number of independent angles, which I will come to later. I skipped a slide, I think. Sorry, I skipped this one. I just wanted to mention the importance of angular distribution and angular correlation measurements, because in nuclear structure studies, you use this to determine spins and parities of states in a nucleus. So you get angular correlation, for instance, in beta decay. If you have 2 gamma rays emitted by your source and you have an angle between theta between the 2, you can have a certain correlation between them. Similarly, in a reaction, you have a direction defined by the beam, or actually the recoiling nucleus, and you measure an angle relative to this recoil, and you would then have the intensity follow a distribution as a function of theta as a sum of Legendre polynomials with your A coefficients that depend on L, the multiple order of the gamma, the ray that you're looking at, also the mixing ratio. Just to explain, make sure that you remember this, your gamma ray can have magnetic or electric character. It carries off a certain amount of angular momentum, and L there would then be given by this relationship between the spins of the 2 states. So you will have E1, M1, E2, or a combination M1 plus E2. And if you have combinations like this, you get a mixing ratio that is defined as the ratio of the probabilities of the higher one, so the E2 there divided by the probability for emission of the M1. And that often is important in determining characteristics of the nuclear structure. This correlation or angular distribution functions, the sum of Legendre polynomials, can look like this. In red, for a pure magnetic, for a pure E1 transition, in blue for E2, and the others show various, the case of M1 plus E2 with various mixing ratios. So you need to measure at different angles that optimize the ability to distinguish between different values of L as well as different values of the mixing ratio. So you need, particularly you need angles at 90 degrees and at fairly small angles as well in order to be sensitive. Sorry, I somehow skipped this one. But anyway, now we're back here. So yes, you need a number of independent angles and you need to optimize your peak to total ratio. So the proposal was schematically something like this, where you would have 8 detectors in the horizontal plane at angles of 31, 70, 110, and 149. And then there's a similar structure at the bottom, of course, detectors at 45, 135, and 90, giving you a good range of angles for measuring angular distributions and angular correlations. That compared to the old Aphrodite frame that had only detectors at 45, 90, and 135 degrees. And keep in mind that your angular distribution is symmetric around 90 degrees, which means that essentially you have only here 2 independent angles in the Aphrodite array, while you have now 4 different angles in this proposed frame configuration. So what do we do with Jean simulations? In the Jean simulation, we first of all have to construct the geometries. So you have to construct the geometry of each individual detector, and then you've got to place them in space in different combinations of clover detectors, lanthanum bromide, and so forth. Your code then emits gamma rays. You can, we selected energies of 1, 5, and 10 MeV. We could also simulate sources and also have gamma rays emitted in coincidence, as well as emitting gamma rays with a specific angular distribution. The code then, the program will then calculate the interactions of the gamma rays in all the materials involved in the whole array, and including the physical processes involved, photoelectric, Compton, and pair formation. And then what you record will be the energy deposited in each element, each detector element. You can also sum it over all detectors of the same kind. You can do this with or without Compton suppression. Now, just for those who don't know, the Compton suppression, if you have a gamma ray that interacts in the crystal, undergoes Compton scattering out of the detector, you will lose that energy. If it then interacts in this bismuth germanate suppression shield on the outside, you reject that event, and that reduces your background. Then we also have, in this case, add back, because your clover detectors consist of 4 different crystals, each an independent detector. If the Compton scatter takes place between 2 crystals in the same clover detector, you can add these 2 energies. You improve both the efficiency, because you then recover the full energy of that Compton scatter event, as well as reduce the background, because if you only looked at that energy, it would give you a Compton scattered event in the background. So this is what the simulated pictures of our detectors look like. Clover detector has 4 crystals in a single vacuum cryostat. each detector, each crystal 70 millimeter long and 50 millimeter diameter. Before it was tapered, it's tapered in order to fit closely together in the middle, and also at the edges here to it's tapered at 7 degrees over a certain region. The lanthanum bromide is very simple, just a cylinder. The large ones, 200 millimeter long by 89 millimeter diameter, and the smaller ones we have at 50 millimeter by 50 millimeters. The suppression shield has bismuth germanate scintillator surrounding the central hole. This clover detector then fits inside this hole so that any gamma scattered out of that, germanium can interact in the bismuth germanate, and you can use that to suppress the Compton scatter events. And I just show here this. Normally, the taper of this collimator in front, that collimator is a heavy metal collimator, mainly tungsten, to shield the bismuth germanate, the BGO shield, from direct gamma rays, and also to restrict the interaction of your primary gamma rays to a central region of your germanium detectors. If it interacts near the edges of the detector, it's very likely that it will scatter out and increase your Compton background. To get these detectors as close as possible to your source, we also investigated tapering the front collimator slightly, so you reduce the volume of shielding, but it has very little effect on the actual efficiency of your system. So this is the shapes of the detectors that we, I don't know why I didn't have that in. Yes, we considered two different opening sizes for your collimator. 35 millimeter was the original optimized one, and then we decided that we could also investigate what happens if we increase the size opening angle, which would increase efficiency. Detector placement. This is just some pictures here. You can see the 4 clovers in their BGO shields on the one side of the beam in the horizontal plane, and we could add lanthanum bromides there. In this configuration, we can have up to 18 clover detectors and 8 lanthanum bromides. There's another possibility having only bismuth germanate, having a combination of bismuth germanate and clover detectors, or just for fun, we also simulated the germanium detectors without shields. Then you can get them much closer to your target, together with some lanthanum bromide detectors. Just to show what the GAMKA can simulate, this is a simulation for europium and cobalt sources. Comparison with experiment. The simulation is actually normalized to the source because the simulation typically overestimates the efficiency by about 20%. So we did normalize, but it gives you a very, very good representation of the cobalt source, the photo peaks, as well as the background under them, both for the europium and for the cobalt. So that's when you simulate the source. So now we have just looked at efficiency in different options of detectors in the array. The first one is you maximize the number of germanium detectors in the array. So they can take up to 18, but normally you would only have 17 because you need space for a target to go into the chamber. This would be used for high spin states, parity, measuring spins and parities, mixing ratios, and so forth. General gamma spectroscopy with nuclear reactions. This is the closest distance that you can get the detectors to the target. And in this case, you could have a target chamber of up to 200 millimeter diameter. That would be large enough to be able to fit a silicon step detector, a CD detector that is used for Coulomb excitation, for instance, where you need to detect the recoil particle. So this is the efficiencies that you get. Note that these efficiencies are slightly higher than the real value, as I said, in the order of 20%. So you can see the effect of increasing the size of the collimator, sort of a 1% change, or change by 1% on the percentage efficiency. Also note that 8 large lanthanum bromides have the same overall efficiency than 17 clovers. However, of course, the energy resolution is much worse. So it's only really used when you need when you're looking at high energies with low efficiency. This is a factor of 2 already. So that's when you would want to use lanthanum bromides. Also, increasing the collimator opening angle does not change your peak to total ratio significantly. You could imagine that if you open the collimator size, you will have gamma rays interacting in the outer regions of your germanium detector, and the Compton scattering out of the detector may be large. Actually, the effect on peak to total is negligible. This again is a relative value. In practice, peak to total ratios that we measure is around 45%. Why did it? It shouldn't do that. Okay, this is if we taper the collimators so that we can push the detectors in closer. We increase the efficiency. This is a relatively small change in the distance between target and detector, but it does increase the efficiency. And the important thing is to compare, for instance, the small collimator opening at the largest backward distance, this one, 35 by 35 at 194 millimeters, to the large opening angle, closest distance. For a single gamma ray, you increase the efficiency by 30%. However, if you look at coincidence of 2 gamma rays, you increase the efficiency by 70%. And if you want to look at 3 gamma rays in coincidence, it's a factor of 2.3 larger, which is extremely important because in complicated level schemes, it's very useful to have up to 3 or more gamma rays in coincidence measured. This one I just put in, it's an example of what you could also do. If you put in only lanthanum bromides, this one would be called ALBA, African lanthanum bromide array. Someone was interested in this. At the closest possible distances, you can get a huge 20% efficiency at 1 MeV and 5% at 10 MeV. So a factor of 7.6 over gain over 17 clovers at 10 MeV. But of course, the resolution is not so good. And then you can imagine the options where you have more or less equal number of lanthanum bromide and clover detectors, and you can simulate their efficiency as well. I won't spend much time on it. That's just to summarize the simulated properties. Efficiency for 17 clovers with your different options for collimator size and distance to the detector. And you can see the how it changes as you go up in energy. It looks as if the effect is not so large, but still it is important at larger energies. Efficiency for 23 lanthanum bromide detectors, you can see the drop, but it is still significant efficiency even up to 20 MeV. And I compared peak to total ratios just to show that moving the detector forward, opening the collimator size does not actually influence the peak to total ratio significantly, so that you do not lose a lot in terms of background. Now, the other thing that can happen if you move your detector too far forward and you open the collimator is that you increase the Doppler broadening. For the 4 different options, this opening angle will change from 19 degrees to 26 degrees, and you can simulate again all the parameters that enter into the Doppler broadening. You can measure the peak width when you have a certain recoil velocity, V over C 1%, 2%, 4%, and 8%. Now, just to put this in perspective, most of the time, the reactions that we have studied at iThemba labs are the kind that give you a V over C, a recoil velocity of around 1%. Therefore, you're sitting in this region where you are below 2 keV Doppler broadening only. That, of course, has to be added to the intrinsic efficiency of the detector. But the difference between different options for collimator and detector distance is not significant. So this allows you actually to increase the efficiency without losing any significant peak to total. So when you study high spin states, large cascades of consecutive gamma rays, you could have coincident summing between the two gamma rays entering the same detector at the same time, adding up, and then you lose it out of the peak that you're interested in. So over here, we simulated a number of gamma rays simultaneously, all with the same energy, just to make the analysis easy. And you can see the efficiency then does drop as you increase the number of simultaneous gamma rays from 1 to 20. It drops fairly linearly, but also you can see that the differences in collimator or detector distances all scale fairly well with the increase in multiplicity. So there's no negative effect of increasing collimator size in terms of coincident summing. It is still small and is normally neglected. Resolving power, we simulated this based on the efficiency peak to total and the Doppler broadening at low V over C, the close distance of the detector and the large collimator is best, but here between 1 and 2%, there's very little difference between the different options. So you can, and then this one, the last simulation is just to look at the angles that we have available in this array. How do they do in terms of angular distribution or angular correlation? So what was simulated here is we took a certain reaction of interest. There's this specific 747 keV gamma ray in benzodinium that had been the subject of serious debate as to what the mixing ratio actually is. Two possibilities, minus 0.47 and minus 1.24. And these two options would give you different interpretations on the structure of the state from which this decay takes place. So what I did is I calculated the two coefficients A2 and A4 for a given delta. Then you put that into your Jean simulation and you get W, the angular distribution function, and it's plotted there as the triangles with estimated 5% error on all the points except the 90 degree, because at 90 degree you have more data points. There it's 3%. And then I compare this with the two curves. The one curve is the theoretically calculated distribution function with delta of minus 0.47 and the other one minus 1.24. What it just shows is that your 2 points here at 30 degrees and 45 degrees are terribly important. And with this this set of angles, you can actually be quite sensitive for small changes in your delta. I say small changes. This is actually since these A2, A4 coefficients depend on the quadratic function of delta, you can have two solutions of delta for the same or for a similar angular distribution function. So this just shows that the angles are fairly well chosen and useful for angular distribution calculations. So now I come to the frame design itself. I'm a bit over time maybe, but almost done. This is a engineering drawing of the design for this dandelion frame, designed by Sean Hendricks of this company. They also did the construction of the frame. And that is the whole array with all clover detectors shown. So you see the different angles there. And this has been constructed and installed at iThemba Labs. Here, the two halves of the array has been opened up to show the target chamber in the middle. This is the whole array, not with all detectors in, but with most of them in. You can see there is the, you open around that line. And this is now complete. There's a small modification needed to the base plate of one of these detectors to avoid any possible deviation when you load a full load of detectors on it. But in principle, that is a small modification that iThemba Labs can and should do in the near future. And then the whole array would be ready for experiments, awaiting beam time. We have proposals for it. We just need beam time and that small modification. And with that, I end thanking the people that contributed to this whole project, particularly Nico for being the lead investigator in this funding proposal. These are the other contributors to that, and a number of other people that played important roles in the whole project. Okay, thank you.